Hi everyone, thank you so much for joining. I'm Fernanda Dominguez. I just started my fourth year as a computer science undergrad student at the University of Sonora in Mexico. And I will talk about my summer research experience with Cross in the Popper project, working with systems performance validation workflows. The purpose of my project was to follow the Popper convention to create a reproducible workflow for a performance report of a high-performance system framework. For this, we chose to use SPDK and its NVMe VDAV performance report. Here, we'll compare the SPDK support engine for NVMe block devices against the normal Linux Livayo engine. We will do this by running the test workloads specified in this report in each of these engines and then compare their performance. SPDK, or the Storage Performance Development Kit, is a framework for writing high-performance storage applications. This is achieved by having direct access to the device by moving all the drivers into the user space. This way, the requests are done directly into the device and it avoids system interruptions, while Livayo does have to use the kernel space and stick to these inconveniences. So this is what the workflow would look like. First, since everything will run inside a container, our first step will be to build a Docker image that installs all the dependencies and already has SPDK and FIO built. Then we will take a step to prepare the device for the benchmarks. Here, we will write the mounting point of the device into the FIO configuration files. We will format the device, and also we need to ensure here that the device reaches a steady state. Then we will run the three workloads specified in the report that are a random read workload, a random write workload, and a mixed workload that will be 70% read operations and 30% writes. And finally, it will generate a PDF with the plots of these results. But before running these workloads, remember we need to ensure that the device reaches a steady state. This is a state where the variation in time is not significantly affecting the results that we're getting. This is important because if we just run it on a device that maybe hasn't been used in a long while or that is new, we might get much better results than otherwise. Therefore, for this problem, we will run something we call a precondition workload. We can specify FIO to collect the measurements every certain period of time or to run a workload until a certain condition is met. So taking advantage of this, we will tell FIO with this configuration file to run this precondition workload and make the steady state comparison each 30 seconds. And that this comparison will be that all the operations per second are within the 1% of the mean of the measurements in this 30-second time window. This way, we will ensure that FIO will be automatically running the precondition workload until the device reaches a steady state. As you can see, automating this part of the process is kind of the key to achieve automating the report. And these are the results plots we're running in the NVMe device that cross-landed me for this project. Notice that tremendous difference between the number of operations when using SPDK, either for reads or writes. Okay, so what goes next? Well, we already have reached out to SPDK team to propose using Popper as a part of the process of releasing this report. And also, it's a good way to get started with testing SPDK. Thank you for your interest, and thanks to Cross for letting me be part of this. To my mentor, Ivo Jimenez, and to Janshin Liu for their help.